Okay, what I'd like to start out with, first of all, any questions from last time? Okay, what I'd like to do is to start out by talking about, by now everyone should theoretically have gotten their project proposal emails back. Is that right, or are we still sending them out?
I'm still sending them out.
Okay, so don't worry about your, don't worry about your grades for grades purposes. Do worry about your, let's say, project, comments and suggestions, so that we know what you're kind of supposed to do next. That's kind of right now the thing that I'm most concerned with. The project progress reports are due in 2.5 weeks. Okay. And I wanted to make sure I got all the feedback back to people before the weekend, so people can start to make progress on it. And I wanted to talk about all the different projects, at least briefly, what the general comments were, so that people can, we can have an intelligent discussion and make sure people see what I'm kind of liking and not liking about certain proposals. Is that fair? When will everybody have their feedback, you think?
In 20 minutes.
20 minutes. Okay, so if you haven't gotten yours yet, I would don't immediately panic. But I want to go through what I saw generically about the different projects. Okay, is this fair? Okay. Several people, and if I had to say what was the biggest thing that in general that I liked or did not like, I liked a project proposals when I felt I was going to learn something by reading the project when it was done. Okay, I didn't like the project proposals when I felt you guys were doing basically just a Kaggle challenge. Several of the projects that groups seemed to like were ones that were using old Kaggle data sets. Okay. Again, there's this thing about wildfires. One of them, the projects was on wildfires. Okay. And, I'm interested, if you're doing a project like that, I don't want you to say, look, the Kaggle challenge said predict this. I am using some fancier algorithm and I'm going to get 2% better than somebody else got. Okay. What I want is a project that's going to tell me something about fires, okay? That's going to be telling me something about, why fires occur and how you would prevent them, okay? I would like to have one that is going to, a good project might be one that looks at the weather in a serious way and tells me why is it that certain conditions are more likely to have fire than other ones, okay? So again, in general, I like people to do things that are exploratory data analysis, okay? And, kind of addressing a larger issue than just a Kaggle score. Any questions about that as a philosophy? I happen to have, actually, at the risk of getting myself in trouble, I happen to have a book in my office about arson investigation. Arson is about setting fires and stuff. How do you tell if somebody has set fire to something? And, why I have this book is actually because I met a guy who wrote the book. It's not that I'm planning anything. But it is clear that fires are very, there's a lot that is kind of known about why fires start and how fire, and I kind of want to see that someone who did this project should be able to have an interesting and intelligent discussion with an author of a book like that afterwards. Any questions? And again, I'd like this to be a discussion, okay? Another fairly large group of teams, okay, ended up picking the project on fatal force, okay? They're trying to figure out something about where police shootings are. And what I generally think is the interesting question here is kind of, where are there what are the kind of the things that disproportionately cause police shootings compared to kind of where you would kind of expect there should be based on other factors on the ground. Okay, let's say that I had a theory that graduate student drivers were not very good drivers of cars. Okay, my guess is that there is, probably, it would not shock me if this is generally true. Okay, I would imagine many of you came from countries where you didn't drive, okay, or situations where you didn't drive before you got here. I can imagine that many of you, even if you did drive, the conditions, the habits of the road and stuff like that are wildly different than you were, than what we have here. If I wanted to do some kind of a study on how good or bad graduate student drivers are, it would be wrong to look at how many people they hit by cars. Why is that? Can anybody think of, would that be the right way to judge whether or not, graduate students were good drivers or bad drivers by looking at statistics of how many times they ran over people and killed them? Who here thinks that would be a good statistic? Who here thinks that that might not be the right statistic to study?
I think that might be a bad statistic.
Why would that be a bad statistic?
So there's a lot less pedestrians by Stony Brook than in the city.
Okay, so one question is that in certain places, there may be more pedestrians than less pedestrians. Okay, and that if you're in a place where, you're saying if you're in a place where the graduate students have a lot of targets to hit, they're going to run down more people. Okay, that might be one factor, but that's not quite what I'm thinking about here.
It's also an extremely rare event.
Bingo. Now, this is what I am concerned about, okay? Now, in order to run down a driver, so if you're a driver and you run somebody down and kill them, you had to be probably a bad driver or make a very serious driving mistake. But you also had to be extremely unlucky, okay? What fraction of, let's say, accidents does somebody get killed in, a pedestrian get run down in? Okay, I'm going to argue very, very, very few. And if you wanted to get a better statistical background of understanding why something is happening or whether there is an anomaly thing, you want things where there's a lot of frequent data. Is that, or you're better off studying the frequent thing. In the United States, the murder rate went down substantially from like the 1960s to today. And why is that? Actually, people debate this quite a lot as to why it is, but one of the reasons is that hospitals got better, okay? It used to be in the old days you could shoot somebody and know that they would die. These days, medical care has gotten better, and a lot of the people you shoot don't die and don't get counted in a murder statistic, okay? So what's the point here? I think that studying police shootings and police violence and policing is an extremely interesting thing to do. But what I do think is that, instead of trying to predict it's important to kind of understand kind of the baseline considerations, okay, of why there are, let's say, would be expected to be more shootings in one area, even if the police were completely unbiased, okay? And, and that kind of analysis I felt was missing from most of these kind of proposals, okay? I kind of want to see that you're trying, in an ideal world, you will be able to tell me something about what communities have policing where there is excessive violence over what there should be. Okay, and that I think is a more interesting question than to say that there's going to be more shootings in this part of the country because that's where the crime rate is higher or something like that. Any questions about that? So in an ideal world, I would like to come away with this to say that you're understanding why there are you know, you really are able to tell me where there is an excessive problem and where there isn't. And it's not a question of what the frequency of police shootings. Why are there more police shootings in Manhattan than in Stony Brook? Anyone give me any theories as to why?
There's like 2 to 3 orders of magnitude more people in Manhattan.
One thing is there are more people there, right? Why are there, there's more, presumably more crime that would have to be investigated, okay? But does anybody, any questions about this? For this to be interesting, I want to know with some subtlety, okay, as to, where there are places that really have problems that are not explained by kind of base methods. Any questions? Okay, good. Now, again, there was another company, again, the ones that seem to be drawn from Kaggle sets seem to attract more people, probably because they thought it was easier to get data, okay? But when it comes to the thing about happiness, okay, what I'm interested in knowing something, I would like to be able to learn something after reading your report about why countries are happy. Some countries are happy and why they are not happy. What countries are happier than they should be? And why is that? What countries are more miserable than they should be? Why is that? Okay. I'm interested in if people are going to add data, new data to it. The question is, I want you to have a good reason why, what you're trying to show in that data. What aspects of happiness are you capturing? And the real question is, how much of it is of these other variables are captured by a generic notion of happiness versus just being another factor you put into some kind of a model. Any questions about that? So if you're doing this one, I kind of want you to have some kind of one or at most one, at least one, but maybe at most 5 things, aspects of happiness you care about, okay? And that's not captured, ideally not captured by the existing data set, and that you can get some kind of a sense, okay? And the report is not going to be, I got a good p-value because I used a fancier modeling method. But by looking at the data, I understand how the world works better. Any questions about that? Okay. The fragile family challenge. This was another thing. Again, I don't want to see people just tell me what family is going to break up, okay, and try to use a predictive model. I want to kind of learn something about why families stay together and why they don't, that you can kind of explain. What are the factors where kids succeed even though they have a poor background? Many people come from poor backgrounds. Sometimes they thrive, they're able to thrive and succeed there, and sometimes there's a bad upbringing and it leads to a bad result. And the question that I'd like to figure out is, again, why is it that some families that don't look like they should succeed, okay, are in fact succeeding? Okay, is it religion? Is it being being poor in a good place? Okay, I don't know what it is. Okay, and that's the kind of questions I'm interested in. Any questions? For the personality type one, again, there was this Kaggle contest here to give you some idea of how to predict the personality type, Myers-Briggs personality type from text. The interesting thing is not to try to get a better classifier on the Kaggle data in and of itself. The interesting question is, can you learn something about the distribution of these Myers-Briggs types on some kind of cohorts? So I happen to find Wikipedia a very interesting thing, okay? You have articles about, hundreds of thousands of people. And could you tell me something about what Wikipedia tells us about what the personality of these people are? And can you do this kind of analysis by groups of people? Does it make sense? Do athletes look different in one sport or another? Okay. Are different scientists, do they have different personality types? How do they look down here? And so I think the interesting study would be some kind of breakdown of Wikipedia people by personality type. How does it vary by gender? How does it vary by nationality? And by historical periods. Okay, and an analysis like that would seem pretty interesting. Okay, and that's kind of what I would love to see the groups do if you're doing the Myers-Briggs thing. Any questions? For the sleep study, again, the important thing is to make sure you get the right data set and that you ask the right kind of questions. Again, I'm kind of interested in seeing how can I see sleep patterns change as a function of the sunrise and sunset time, as a function of the time zones, okay? I would argue that bedtimes are presumably affected by this, okay? I would argue wake-up times are presumably affected by this. And it's important to me that you come up with a methodology where you kind of can show this, okay? These factors have to exist. The question is, can you show me and convince me that you can tell with that? Now, it might be that you need to have, instead of samples of tweets, 1% of the tweets of everybody in the universe. Maybe you need to have the complete tweets of a small number of people who tweet a lot, okay, and see how their schedules shift, okay? I read an interesting analysis of Trump's tweets and sleep wake cycle as being told by tweets, because he tweets a lot and he sometimes does it in the middle of the night. And, you know, they could make all kinds of interesting predictions from that or observations from that. So I'm kind of interested in my dream is that you're gonna give me some kind of a high resolution sleep map, okay? Or as a function of time, maybe distinguishing the US from other places, okay? And again, I want to learn something about how and why people sleep here, okay? That is interesting here. Any questions about that? So you got to figure out what's the right data set that can get that for you. On the genome project, there were, again, my concern here is, here is the Covert genome. My belief is that there are very small regions, probably one or two, that are unusually resistant to having mutations. Okay, mutations should happen a lot in viruses, okay? And that these are going to be very special regions that that there is some kind of biology explaining why the sequence here is so important. And part of this is getting the data on tens or hundreds of thousands of different sequences, doing some kind of an alignment and properly interpreting where the mutations are. And also getting some kind of an understanding, a little bit of an understanding of the biology, what's going to cause things, okay? There are certain concepts that might explain why certain regions don't get hit. And that's what I kind of want to see you do. Any questions from this groups? From the trust in polling data, again, I kind of want to get some kind of a, some kind of an analysis of why do people trust and how does it vary by groups, okay? Part of that is an exploratory thing. Part of that is getting a good index or score of trust from our data. And some of you found some interesting data. If you don't have the data from our poll yet, you can correspond with this gentleman and they can get you some of the data we have on polling. Any questions? for the books in movie scripts, again, the goal was that here you had a book, here you had a movie script. What parts of the book were used in making the movie? Okay, that kind of thing. And you know what I want to see, some group, so one group had one script and one book, and we're doing an alignment from it, and that was potentially interesting. But I want you to make sure you get a sizable number of pairs, so you do something general. I want to see at least 10 book script pairs. Okay, I want you to study how good your alignment was. That particular group showed me an alignment, okay, but they didn't. I don't have any real way of knowing how good it is. Would you have gotten the same thing if you aligned the script to The Godfather against Harry Potter, the book? Okay, you might very well have. But I guess when you've got enough book pairs and you can see what alignments are real and what alignments aren't, that would then be interesting. Any questions about that? Any questions about any of these, the projects, or what I kind of want to see for progress reports? I want to see some intermediate, some evidence that you've really kind of started doing some serious experiments, that you understand what you're doing, and I look forward to seeing that then. Any questions about projects? Okay, going once, twice.
Hello.
Sir,
Yes.
I had a question about the books and the movie script project.
The
So
movie script
you have
project. Okay,
written
yeah.
that 14 books. So you have written that 14 books. You can manually check whether the unmatched sections are really unmatched. So we are kind of talking about some sections of the book which are left out, right?
Right.
And okay, so we are supposed to actually check manually if these are
Well, there's a
really
difference
left out.
between checking and
And a
validating it.
more complicated,
It
Okay.
seemed to me that if you were saying a whole episode in a book was not there, could you look very, very carefully for the words in that section to see if they appeared anywhere in the book? What made it, what was an example of the story, or what was going on in this section and it isn't in the original book? I think that there's a certain level of looking at this that you should be able to do, okay? And that when you're doing an alignment, you should be able to come away with yes, it is right, or no, it is not right, or it's kind of fuzzy, or So I think that it's perfectly fair for you to have some kind of exploration. How many people are in your group?
2.
2. Okay, so now we're talking, could one of you look at 5 books and 5 scripts that you've aligned? And the question now, if you look at where there are hunks that you're saying are deleted from the book, you don't think you could find a way using computer search tools or something like that to decide that it really was deleted or wasn't deleted? I think that that's a doable thing, okay, to some degree of resolution, okay? And there's a difference between saying this is what my algorithm got and looking at it and seeing whether you really believe or trust or like what you've seen. And that's kind of what I'm encouraging people do.
Okay.
Any other questions?
I have a question about the happiness.
Happy, yes.
Yeah. So, like we could basically look at the rankings and see if like some of them don't make sense. So we could come up with a new way to rank them with other data set that would be augmented into this.
Okay, now when you say don't make sense, what does don't make sense mean?
Like based on the other other data that we might have about the country, we just, I mean, I don't know, maybe we could take a survey and find out if people would agree that the ranking is okay.
Well, there's a question of whether knowledgeable people know what it is. Okay. Do I have a good idea of how happy they are in Bolivia? I have no firsthand evidence of how happy people are or are not in Bolivia. Okay.
Yeah.
But the question of saying that, well, look, there are a bunch of countries which seem to be unusually happy relative to, you know, something like economic conditions. Why is that? That's now an interesting question. Okay.
Okay.
And that's something I would like to know.
Okay.
Okay. Any other ideas or questions? Basically, I want you to, in general, I want you to pretend that you're scientists and try to learn something from the data, not just get you know, try to test yourself by whether you've got a model that gets a high score. Okay. That's kind of my biggest single criteria thing. Now, some of you, after thinking about it, the important thing is, do you guys know what you want to do next? Okay. Some of you may have written your proposal. Maybe I didn't like it too much, or maybe after looking at it, you didn't like it too much. If you want, there's no reason why you couldn't change. Okay. Especially if you haven't done very much on your project so far. Okay. But that's up to you. Okay. And again, of the projects that I, you know, of the two of my favorite of the projects that I listed, nobody picked. One of them was on the studying what people pick up, which objects people pick up at a grocery store. Okay. How people empty carts or manipulate things. And the other one was on this basic idea of looking at videos and trying to get properties of the people from analyzing something about their appearance, or something about the audio, or something about the text. Okay. But you guys think about it. Hopefully you like your project. Hopefully you know what to do next. And if not, you can come and talk to me about it. Any questions about that? Going once, twice. Okay, let me now go back here. Boom and boom. Okay. So what I'd like to talk about now is, let me try. Actually, hold on. Okay, let me try this here. So I'd like to, you know, start getting into some of the more machine learning aspects of this thing. But one thing I'd like us to do, because we're going to talk a lot about linear regression and things like this, I want us to review linear algebra a little bit. Okay, I know everybody has had linear algebra. I think everybody knows, you know, kind of that by now for your project or anything else, most of your work is basically building some kind of a data matrix. Typically in your data matrix, the rows are examples. When I think about a matrix, I think of the rows as being examples or records. I think of the columns as being features or attributes. Okay. A lot of machine learning is working on matrices. And so I do want us to quickly review a little bit of linear algebra. Okay. And the stuff that I think it's important that we kind of know about now. Any questions? Okay. So the first thing that's important to recognize is that an n by m matrix can an n rows by m columns can represent many different things. And in this class, we might actually use all these different kind of ideas of what the representation is. One is as a data matrix. That kind of makes sense. One way to think about it is that a matrix kind of represents a point set, a geometric point set. If you have an n by m matrix, you can think of it as being n points, okay, in m dimensions. In m dimensions, okay? And it's often very, very useful to think of, you know, our data set as being points. We're going to talk about nearest neighbor methods. We're going to talk about other things later on. But so we should realize it can represent points. We can also represent systems of equations as matrices, where if we have an equation, you know, 3x1 plus 2x3 equals 7, we could represent the system of equations where every row represents an equation, every column represents a variable, and the data is the coefficient, okay, of that variable, okay? And that's, again, obviously you've done Gaussian elimination and things like that. When we talk about doing, you know, linear regression, we're kind of starting to think about systems of equations on some level, or we could think of them as points, something like that. You can represent graphs by matrices. Everyone knows about an adjacency matrix representation. If you have a graph of on n vertices, okay, element ij of the matrix can tell us whether how many edges there are from vertex I to j, or the weight of the edge from I to j, okay? And vectors are kind of natural things, okay? A vector is kind of a one-dimensional array, okay? And kind of when you were studying calculus, you learned about vectors. You learned about the, you know, them representing directions or something like that. And so we can interpret any row or column of our matrix as being a vector. Any questions? Okay. Now, you know, there's certain areas of mathematics I liked when I was taking them in school. There's certain areas of mathematics I did not like when I was taking it in school. Linear algebra was one of the things I did not like, okay? And the reason I did not like it was that I'll admit I didn't find algebra very intuitive, okay? Algebra, okay, is a, you know, kind of a way of, you know, kind of, you have this kind of system of mechanical operations you can use to manipulate formulae. I have a hard time capturing in my head the intuition of these formulae, okay? Does anybody recognize this? What is this below here?
Isn't that the equation to find the weights for linear regression?
This is an equation to solve linear regression, okay? Intellectually, I know what linear regression is. Intellectually, I know what it is. Intellectually, I have seen the proof where these things have, this thing popped out of it. I don't tend to see, though, why this is, okay, the way to find the optimal set of weights in linear regression, okay? So one thing that I found when I was doing linear algebraic proofs, okay, when you did linear algebra, okay, it is, you know, you're kind of used to something being set and then there being a lot of algebraic substitutions that you're doing. And then magically you end up with a formula at the end. It's often, I never really tended to think like this very well. How many of you have seen the proof that 2 equals 1? Here is a proof of 2 equals 1. Does everybody kind of see, if you look at this, every step in this algebraic thing makes sense. But why isn't 2 equal to 1? Does anyone see what the problem in this algebraic proof is?
In the case that a minus b is 0.
What?
In the case that a minus b is 0.
Well, you're saying in the case where a minus b is definitely going to be 0 if a equals b.
Yeah, but you do a division by 0.
Okay, so somewhere in here I'm doing a division by 0. Where am I doing my division by 0?
Line 4.
Okay, I think it's going from here to here is the state of sin. Everybody kind of see that? I find it hard to pick up on these kind of things. It looks mechanical, but there are constraints on these things. Okay? So again, when we're dealing with linear algebra, everything looks great when it works. understand that there are special cases like singularities, okay, where they're like division by zero. Suddenly, you know, everything worked except in this kind of a case, okay? And in linear algebra, the kind of division by zero case typically is when you've got matrices that are called singular matrices, matrices that you can't invert, okay? And bottom line is, when I'm going to talk about algebra, linear algebra from now, I'm not really going to talk about it from a level of proofs. I'm going to talk kind of about what the operations that I would like to see us be able to do that are useful things to do with linear algebra, and try to just refresh ourselves what kind of things we can do with them. Okay? Okay, so one thing that's true is we said that a vector kind of corresponds to a direction. We said a matrix corresponds to what you call it, could be thought of as being each row representing a point in d dimensions. One way that we could represent, let's say we have a set of m examples. We can think of the data for that as being, you know, m points, each in d dimensions. We could represent them, each one of these rows, as a point, meaning just a point somewhere in d-dimensional space. Sometimes it's more useful to represent them as unit vectors and magnitudes. What is the idea here? The unit vector, if we think about what a point is, if we take the origin of our space at any point, it defines a direction. It defines kind of a ray from the origin out. If we take a unit length sphere, a sphere of radius 1 in d dimensions, okay, around the origin, we could represent the unit vector is basically going to be the coordinates of the point of intersection between that that sphere of radius 1 and the ray through that point. My claim is we can represent any point as a a unit vector and a magnitude. How many times the unit vector do you have to go to get to the original point? Okay. Why is it sometimes useful to represent data as a unit vector? A unit vector could be kind of thought of as a normalized data set, right? You took the data values and you normalized them in a way. So somehow that none of the magnitudes of any dimension were too big. Okay. Why, can anyone give an example where it might be more useful to think of a normalized value? Okay, a representing the item as a unit vector instead of as the full points. Okay, specifically for the purposes of comparison. Okay, let's say that we had I'm going to say just as an example. Okay, a common thing in natural language processing might be to take each document, D1 through DN, okay? And you may represent it by the frequency of how many times it uses each word in the language. Let's say we consider the 20,000 most popular words. We could count for in document how many times did each word appear. Okay, this word appeared 3 times, 4, 7. Okay. Does everybody see that if we take the word counts like this, every document appears as a point in 20,000 dimensional space? Does everybody kind of see that? Now, if we wanted to compare similar documents, we could look at which points are similar, maybe by not being too far apart, or we could compare the unit vectors. Why might we be better off comparing the unit vectors than the actual vectors of counts? If we wanted to tell whether documents are similar. Anybody there?
Yeah, I'm sorry. Could you repeat that?
So the question is, okay, recognize that if, again, let's think we were representing books as documents. We could represent each book or each article by a, what you call it, a, how many times did each word appear in the text? Maybe dimension 1 was cat, dimension 2 was dog, okay? We could compare the absolute counts. And now every book is going to be a point in absolute count space. And we could now tell whether or not two documents are similar by comparing the points. We could compare the points, or we could compare their unit vectors. Why might it be better to compare the unit vectors than the original points?
Because I think it avoids some of the messiness with high frequency words with the and a and their participles.
The and a, well, actually the high frequency words probably would still be high frequency words if you, once you normalize it, right? So if there was a the dimension was high, probably everybody wants to be high in the coordinate. It's still going to be high in the coordinate. What is the difference here if we have this thing properly normalized? I'm going to claim it's going to be about the difference between long and short texts. If you have an article about football and a book about football, we would expect the distribution of the words that they use are going to be very similar. But if we look at absolute counts, a short book on football is going to be quite far in terms of absolute counts from a long book on football. And it might be the absolute counts might be closer to what you call it, a long book about, you know, basket weaving or something like that. Okay. So anyway, sometimes we are interested in fairly often comparing the vectors, okay, defined, the unit vectors defined by data instead of the raw data fields of the matrix.
That's
And
it.
one way to you know, let's say, talk about comparing vectors is to think in terms of the angles between them rather than the Euclidean distance between them. Okay, and this is kind of an let's say a generally useful way to compare vectors. Okay, in linear, when you took linear algebra, okay, you learned that the cosine of the angle between two vectors was the dot product of the two vectors divided by the magnitude of their lengths. Okay, and what do we know about cosines? The cosine function is kind of, if we remember our trig, what is the cosine of an angle that is 0? Okay, the cosine is 1. What is the cosine of an angle when they are as far, vectors are as far apart as they can be? Okay, what is that? That's going to be -1. Okay, and if you have two vectors that are kind of orthogonal to each other, independent of each other, you get a cosine of 0. Okay, by this measure, cosines, the cosine function is has the same property as our correlation coefficients. And so when we're computing the distance between vectors, okay, we don't get actually, if we compute the cosine of the angle between them, we get something that's more like a correlation coefficient. And basically, it reduces to computing a dot product of the two vectors. Okay? Again, they've got to be properly normalized by length. But if these were unit vectors, okay, then then the normalization didn't do anything. So basically, just taking the dot product of unit vectors gives us something that is like a correlation coefficient. Okay, and that's one reason why place where linear algebra comes in here. Any questions about that? That is something that people should know. Okay, I want to talk a little bit about operations on matrices. And for the following examples, I took as matrices data from two pictures. The thing on the left was President Lincoln. The thing on the right is the Lincoln Memorial. Okay? And so I want us to think about these as like 512 by 512 matrices of numbers, but we can kind of view things in the pictures, which we can't really see in numbers. Any questions? So that's going to be my ongoing examples now. One operation that is very important in manipulating matrices is the transpose. Okay, the transpose of a matrix basically interchanges its rows and columns. So the first row of this matrix becomes the first column in the next matrix. Okay, so we know that the transpose, M sub ij transposed is M of ji. Okay, and so a transpose turns an A by B matrix into a B by A matrix. Okay, that I'm sure is an operation people need to know. Okay, once you can take matrices, you can add matrices. You can add matrices to its transpose. You can do linear combinations of matrices by adding different fractions of different matrices. This is kind of a way you can kind of, zoom in from one to another. Okay. Any question? That I think is pretty obvious. Now, the most important thing, operation, I think data science wise, on matrices is basically related to matrix multiplication. I talked about the dot product of two vectors in terms of, when we were talking about cosines. The dot product of two matrices is basically going to be, if I have two matrices, okay, both of which contain n elements, it's the first element of each matrix of each vector, the products of the first plus the products of the second plus the products of the third. So the dot product Cij of the ith row of a matrix times the jth column, okay, of another matrix. Well, okay, this is a product matrix. But basically, the dot product is the sum over all the length of the common dimension of the ith element of one times the ith element of the other. Okay. If we are multiplying two matrices, what we are really doing is getting an array of dot products. Okay. And so in general, here we have an example of a 2 by 3 matrix. Here we have a 3 by 2 matrix. Dot products only work when the inner dimension is the same. Okay, but if the inner dimension is the same, you can multiply an x by y matrix times a y by z matrix, yielding an x by z matrix. Any questions? And recognize from what I said before about the cosine thing. If the cosine, a dot product, if the elements of one vector are big when the elements of the other vector are big, the dot product is large. So this is why dot products kind of measure notions of correlation between things. Okay. Any questions? When you took linear algebra, you learned that there were properties of matrix multiplication. The matrix multiplication was the same. You could parenthesize things however you wanted, and you would get the same answer. But you couldn't commute. You couldn't take the matrices and swap the order of them. Taking two matrices and swapping them and multiplying them would usually yield different answers. Okay. The other property about matrix multiplication that's important is that there is an identity matrix. Okay, if you have ones along a main diagonal and everything else is 0, multiplying any matrix by the identity matrix basically yields the original matrix. Any questions about this? I know you've seen this before, but I just want to kind of refresh this because we're going to use some of these things soon. Now, as far as how you do matrix multiplication, okay, the algorithm that you guys were taught in school, which is basically for every row and column, do a dot product, okay, is, kind of if you had two n by n matrices, okay, that was an n cubed algorithm, okay. There are faster algorithms of it theoretically. So you may be used to things like Strassen's algorithms and things like that. The truth is that there are libraries that multiply matrices extremely fast. Okay, this is one of these worlds where, if you use Python, okay, there are optimized C language libraries for multiplying matrices that are, remarkably fast and remarkably numerically stable. So, many things you can kind of express as matrix multiplication or as other kinds of logic. And the matrix multiplication is so fast that sometimes it's easier to just multiply matrices than do logic with matrices. So that's one of the things to keep in mind about matrix multiplication. When we think about matrices, okay, feature matrices, multiplying a matrix times its transpose is an interesting collection of matrices, which we call covariance matrices. What happens if I take a feature matrix? Let's say I have a matrix of n rows by m, and I transpose it. So now I've got m rows and n columns. Okay. Okay. When I do this thing, I am going to get an n by n matrix when I multiply them. And the dot product of multiplying a matrix times its, a row of a matrix times a column of a transposed matrix. That means that I'm basically going to be dotting one row of a matrix with another row of the matrix. Okay? So A times A transpose is an n by n matrix that is going to measure how similar rows are. A transpose times A is going to be in this case, D or M by M matrix that is going to tell me how similar each pair of columns is. Okay? And so the covariance matrices of a data set tell you a lot about what the similarity structure is. When I took the dot product of the Lincoln Memorial times its transpose, okay? Every element here in the covariance matrix, the covariance matrix here, M sub ij is going to be reflective of the dot product of the ith row and the ith column, of the ith and j rows of the original matrix. Why is it that, if we look at these things, the covariance matrices look symmetric? Why is the covariance matrix symmetric? Anybody?
It's because the operation is symmetric.
The
The
operation
10th row.
is because
Yeah.
this is comparing here the ith. What is the dot product of the ith row with the jth row? This one over here is comparing what's the jth row with the ith row. It's the same thing, right? So the covariance matrices are symmetric. And if you think, look at this kind of thing, you do see it kind of capture the structure when it's comparing the rows with the rows. All the rows in this world are incredibly similar. That's why you get this matrix of high similarity. Okay? All the rows here are quite similar to all the rows there. Why is it that these are lighter than that? It's because this thing had more dark in it. The covariance matrix is not normalized, okay, for magnitudes. It's just sort of dot products. Correlation coefficients had to be normalized. Remember, they were divided by the standard deviations of the variables, okay? But it is clear that when you look at the covariance matrix here, you're seeing the structure of the rows. When you look at the columns of the Lincoln Memorial, the covariance of the columns, it should be clear that you get a high dot product whenever you have two columns that are from the dark parts of the rows, okay? And that's what these dark things are. You get light dot products whenever you're comparing two white sets of white columns, and that's what gives you the white streaks. Any questions? Do people see how you see the structure of the, of the similarity of the rows or the columns in the covariance matrix? Okay, any questions? So there are many other ways to interpret matrix multiplication. And this is kind of one of the reasons why matrix multiplication is an important operation to kind of know about, okay? In graphs, what do you get when you multiply an adjacency matrix of a graph, okay, by an adjacency matrix of a graph? If each value of the adjacency matrix was 1, if there was an edge there, if I sub j, element I sub j is going to be, if we have an edge ij and an edge jk, when we took the dot product of the ith and jth, when we squared it, okay, the m sub ij times m of ji is going to be 1 if and only if both the edges were there. And so when you multiply two adjacency matrices, what you're really getting is a count of how many paths of length 2 there are between different vertices. Okay? That's one thing that's interesting about it when you interpret the matrices as networks. Another thing that's interesting is that there are, if you have a matrix that has a 1 in every row and a 1 in every column, this thing is called a permutation matrix. The interesting thing is that if you want to rearrange the rows or columns or the rows and columns of a matrix, okay, what you can do is multiply that by a permutation matrix. And so some rearrangement operations are basically done by matrix multiplication. the thing that I find interesting is that if you're trying to do have to rearrange the rows or columns of a matrix, I would instinctively, as a programmer, think about doing it in an ad hoc way. Maybe like take the row matrices and for I goes from 1 to j, copy each element into another matrix. If you use a very highly optimized matrix multiplication library, it will be faster to do the rearrangement by multiplying by permutation matrices rather than than doing the ad hoc logic, okay? Because matrix multiplication libraries are good with dealing with sparse graphs, okay, sparse matrices, okay? So anyway, so there's a lot of operations that can come from matrix multiplication. Any questions? Comments one way or another? There are other interpretations, okay? If you view these points in space, there are matrices that when you multiply a point by, kind of rotates that point in space about an axis and stuff like that. So certain geometric manipulations are easy to do basically as matrix multiplication. Okay, and that is sometimes a useful thing for us to be able to do. Okay, what is the inverse operation to multiplication? We're used to knowing about adding and subtracting are kind of, inverse operations. And multiplication and division are inverse operations. So when we talk about matrix inversion, an inverse of a matrix, if you have a matrix A, an inverse of a matrix is the matrix A to the minus 1, such that A times A inverse gives you the identity matrix. Okay? And what that kind of means, if you manipulate this thing, that the inverse of the matrix is really the identity matrix kind of divided by the original matrix. Okay? So when we think about division of matrices, what we're really thinking about is the inverse process. What is the matrix that when we multiply by A gives us the identity matrix? Any questions? How do we find the inverse of matrices? You learned this when you took a linear algebra course. There are a couple of different ways of doing it. For certain small matrix sizes, there's well-known formulae that will do that. In general, the way that I think is easiest to find the inverse of a matrix is you build a matrix. Okay, you by taking the original matrix you want to invert, append it the identity matrix. Then, by using Gaussian elimination, let's say that we want to turn what was the identity matrix. Okay, we want to do a combination of row and column operations so that the first half of our matrix is now the identity matrix. If we do the operations to both the data matrix and the same operations to what we appended onto it, the matrix that you get at the end, okay, is the inverse, okay? And so if we have a matrix, we can find its inverse by basically solving a linear system of equations using Gaussian elimination, which is one of the things that you learned about. Any questions about that? So it should be clear matrix inversion is important. It should be clear that you can find this by using, solving systems of equations. Okay. This is what happens. I found it interesting. What does the inverse of a matrix look like? This is the inverse of Lincoln. Okay. Obviously, I don't see very much here that is descriptive to it. But when I multiplied Lincoln by his inverse, this was the matrix I got. Does everybody see that there is a strong main diagonal, which I would associate with the identity matrix? Why is there this other stuff when I multiplied Lincoln by his inverse? Why do I see these other stripes here?
Decision issues during computation.
Say that again.
Floating point precision issues. So we are not getting 0, instead we are getting some value there.
Right, so you're saying this is basically a numerical computation issue. That again, when we are doing operations on matrices, we are doing things with numerical values, floating point numbers. There is a limit to the precision of the computations. These are presumably not zeros, but very, very small numbers, okay? And we have to recognize that when we do these operations on matrices, okay, we will have potential precision issues. Any questions? Okay, so what is interesting, matrix and invert, we saw that we could solve we could find a matrix inverse by solving a linear system. In fact, actually, once we have done an inverse, okay, we could that's really the same as solving a system of equations. What if we have an expression like this? Here we are saying we have a vector of variables. We have a matrix of coefficients. And we have a, y values. That's what the vector here is. Solving a system of equation is figuring out what are the x values, such that a times x equals b. If we take this formula, multiply both sides by the inverse, okay? A times the inverse becomes the identity. This reduces to x times the inverse of a times b, okay? So solving for the values of x is equivalent to basically doing an inverse and multiplying it by the y value, okay? And this is sometimes a useful thing when you want to evaluate a set of equations on a lot of different y values. Okay, any questions? Okay. One property of matrices that is important is that, again, if you're doing Gaussian elimination, you know that, or solving equation, you know that if you have n variables, you'd better have n equations. You need to have at least as many different equations as you have unknowns. Systems of equations are underdetermined if these rows are not linearly independent of them. Okay? If I give you an set of equations, x plus y equals 1 and 2x plus 2y equals 2. This is really one equation. This isn't two equations. The rank of a matrix, okay, is a measure of how many of its rows are linearly independent. Okay, how many rows are linearly independent in this matrix? And where we get into trouble with matrices is when we do operations when the rank is not n. Okay. This is when we start getting into these problems of matrices that can't be inverted and things like that, okay? So the rank is an important thing. When I computed the ranks of my matrices, if you remember back to my Lincoln memorial, okay, I found that when I tried to do some operations on this thing, I failed because these rows are so similar to each other that in fact they were not linearly independent, okay? My picture of the Lincoln Memorial did not have a rank equal to its dimension. And that's why when I showed you, inverse of Lincoln, I showed you the inverse of Lincoln and not the inverse of the memorial. Because unless I have a matrix that is an n by n matrix of rank n, I can't, invert it. Okay. Any questions about that? Again, I know you've seen this before, but I think it is helpful to see this again, just so we're thinking about it and talking the right way. Suppose you have a
Professor, I had a question about rank.
Yes.
So let's say we have a system of linear equations where we have 10 variables and the rank is 8. So there are 8 linearly independent equations.
Yes.
That is still an underdetermined system, right?
Well, when you have actually 8 equations and 12, okay, the answer is yes. When you have 8 well, let's just think about it. It's like saying that you have the special case here. If we think about what we know, if we had 2 variables, 2 unknowns, and 1 equation, we couldn't solve it. So this was an underdetermined case. This is why if you have 2 unknowns, you need to have 2 equations to do it. And they've got to be independent equations. The rank is measuring how many independent equations we actually have here. Okay? And unless we have a rank that is higher than the rank that's equal to n, we have an underdetermined problem. Okay? Does that answer your question?
Yeah, it does. I mean, I was a little bit confused because in the previous slide you wrote that the equations need to be linearly independent for being, for not being underdetermined. So that's why I was a little bit confused.
Okay, I'm not hearing what you're saying. If you're happy now, I'm going to leave it at that. But
Oh,
or is there
okay,
a correction need to make? Okay, good. Okay, one important interpretation of matrices that that I would like to talk about is this idea of factoring matrices. Many machine learning algorithms, okay, kind of can be thought of as taking a data matrix and factoring it. Okay. What happens if, what is factoring? How do I factor the number, give me a number 72. What is factoring 72? It's coming up with 2 integers that when you multiply them together, give you this. Factoring a matrix is you're given an input matrix A and you want to construct matrices B and C such that A is equal to B times C. Okay. If you are given a matrix, okay, and if you can factor it, what interesting things happen if when you let's say if A is if your original data matrix was n by m, the products are if we're going to factor A, we're going to have to assume B is going to be n times some dimension k, and C is going to be some dimension k times m. Okay. If k, the inner dimension, is small relative to what A is, we have kind of compressed the amount of information we had in this matrix. Does everybody see that in a dream, if I had an n by n matrix, if I have an n by n matrix, this could be expressed as an n by 1. It's possible. If you took an n by 1 matrix and multiplied it by a 1 by n matrix, you would get an n by n matrix. If you were able to take your matrix and find a factorization where the number of the intermediate dimension was small, you have greatly compressed your data. Okay. And more to the point, okay, these compressed data matrices will tell you a lot about the individual, the individual, the original data item. Let's say that we have a data matrix where, I'm going to think back to my natural language problem. My rows, I have n documents, and my columns, I have m different word types. Word 1, word 2, ... word m. And I give you something like the frequency. My data matrix A sub ij is going to tell me how often did the jth word appear in my ith document. Perhaps these have been normalized so they are frequencies, don't have to be actual counts. But does everybody agree that my number of documents by number of words matrix, okay, tells me a lot about each one of these documents? What happens if I could take my matrix and factor it into an n by k matrix and a k by m matrix, such that this matrix B times C, okay, gave me something that was very close to my matrix A. These matrices here are very, very useful as features, okay? That if you think about it, this matrix is going to have on this dimension the number of documents. I could think of this matrix as a feature vector, a k-dimensional feature vector for every document. Okay? So instead of having an m-dimensional feature vector for each document, this first one would be only a k-dimensional feature vector for the document. And if I have that, that's actually a good thing. It's easier to work with something if I have smaller number of dimensions. Likewise, this other matrix C that I'm multiplying B by C by to get A, this is going to be K by M. I'm going to claim that this is going to be, I could think of each column here as a k-dimensional feature vector for what each word means. So what's interesting is by factoring this word document matrix, I end up getting feature vectors telling me what the documents mean that are concise, and feature vectors for the words telling me what the words mean that are concise. And so a lot of building kind of good features, okay, that you can, let's say, use and interpret in certain ways. These things reduce to kind of thinking about, let's say, factoring matrices. Any questions about that? Okay. So this is why factoring matrices comes up in data science a lot. And again, there are several ways, but factoring matrices is not a clean problem. Okay. Factoring integers is kind of sort of a hard problem, and it's sort of presumably an NP-complete problem, although people don't really know it yet. Okay, it's not an NP-complete problem. Presumably, it's a hard problem. But when you took linear algebra, you did learn about certain matrix factorizations. Okay, you probably learned about LU decomposition. Okay. LU decomposition was factoring a matrix M into matrices L and U, which did have interesting shapes. Okay, I wanted it to look like this and this, but in fact, the way it worked was that they were two triangular matrices that you were multiplying. Okay, so when you did LU decomposition, this was you did this in class, back in your linear algebra class. This was an example of a matrix factorization, okay? I could turn any matrix into an L and a U, such that L times U gave the matrix. This is the LU decomposition of the Lincoln Memorial. Because when you're working with these kind of things, the rows and columns, it's often better to in the course of solving this thing, to permute the rows and columns. This is really permuting the rows. So if you look at it, each one of these rows is in fact a row of the Lincoln Memorial. But the order was given at the end by a permutation that you would have to apply to this to straighten it out and give you the original one. Okay? But what was interesting is that when you did this LU decomposition, okay, basically the product of the diagonal matrices, elements of the U matrix, gave you what was called the determinant, which I know you heard of. Whether the determinant is of the matrix was 0 was telling me whether the matrix was a full rank or not. Okay, so this is a way that you can tell whether your matrix is, you know, a full rank or, you know, non-singular. Okay, any questions? Okay, okay, that's where I think I want to end now. Okay, so again, I think we've started reviewing these things, the basics of linear algebra. Next time, I want to talk a little bit about basically eigen values and eigenvectors and where they fit into the world, because there's some interesting matrix decomposition techniques based on that. Okay, and then I want to move on to linear regression. Any questions about this? Okay, if not, thank you.